this module, we're going to talk about viscoelasticity, which is a specific mechanical property that many polymers exhibit. All right, so what is viscoelasticity? So this is a property of a material in which they exhibit both elastic properties, like we've talked about with metals, but also viscous behavior, which you might think of more as a liquid behavior. And so the example, a good example of this is if you've ever played with silly putty. If you ball it up, right, into a ball shape, you can actually bounce it and it keeps its shape, right? So it bounces off the ground and rebounds, and therefore it has to deflect and it has to elastically deform to do this. So it has elastic behavior, but it also has viscous behavior, because if you leave that same ball on the countertop or in the little holder, the little egg that it comes in, then you'll notice after a while it becomes a puddle, right? So it's able to viscously move like a liquid over time. So this is both elastic and viscous properties, and it exhibits in one material. All right, so how we kind of visualize this is by looking at the two types of responses. So an elastic response we think of as instantaneous and reversible, right? So here's basically time versus load. So basically what this is saying is at time TA, we apply a load, so it goes from 0 to this load up here, and we hold that load until another time we reverse it, and that's TR, and we basically unload the material and it goes back to 0 load. So if we want to look at the response, the strain, we see that at that same time TA, the strain goes up instantaneously and is held for the entire duration, and then it reverses instantaneously, right? So the strain follows the load exactly in this instantaneous and reversible manner. So you can think like a spring. If we want to look at a viscous response, if we have the same type of load that's applied from TA to TR in time, what we would instead see on the strain is a gradual increase in the strain over that time period. So this is the viscous part of it. And so when we talk about viscous behavior, it's a delayed time-dependent response, and it may not be fully recovered. So this is, again, like the silly putty kind of settling in its container. So when we combined these two responses for a viscoelastic material, because this is the viscous response, this was the elastic, so when we put those two together, same load, but we have a viscoelastic material, we see that there's an instantaneous jump in the strain, but then we have this time-dependent part that constantly changes over TA to TR, and then it instantaneously drops back, but it doesn't go back to the original strain because we have that viscous portion. So it's almost like the elastic recovery where we had plastic deformation in that case, only this is much more time dependent than the plastic deformation that we've talked about before. All right, so we can test this viscoelastic property with what we call a stress relaxation test. This quantifies the amount of viscoelasticity. And basically what this is you can visualize it as part of a tensile test. So basically we strain the material to some initial value of epsilon naught, and then so we're basically moving the crosshead to apply a strain, and then at a certain point we stop it. So we basically hold it at a given strain. And what we do in this case is we impose the strain and we observe the stress over time. So here you see that initially the stress is here, and then as we've starting to hold the strain here, so nothing's changed, it's just held at a certain amount of strain, we see that the stress actually goes down in this case. And so in this case, we're kind of doing the opposite test where we're imposing a strain and measuring stress, and we see that the stress goes down or relaxes, and this is a time-dependent feature. And so we can look at what we call a relaxation modulus, which is the time-dependent elastic modulus. So if this was a purely elastic material, then this should just be constant, right? The stress should be constant, and we wouldn't have this decay, and so it would just be one value. Here, it's going to decay, and so we want to look at, with viscoelasticity, how does it relax in that case? And so we can define it, this relaxation modulus, as E sub R, R for relaxation, and then parentheses T for time, so it's time dependent, and we see that we put the time dependent stress here over the strain that we're imposing, so this value up here. All right, and so let's look a little bit more at this relaxation modulus. So what we do is we typically, as you see here, the stress is at a given time, and this changes. So we have to typically impose a time for this to happen. And so here you see in this plot it says the relaxation modulus for 10 seconds. So we look at what the value would be in stress at 10 seconds. So you have to define a time for this property. But what we see is that this relaxation modulus is also going to be a function of temperature, because we know that as things go closer and closer to TG and beyond, that there's more viscous behavior. And so this is what this graph is showing you, is that in this, basically in this region up here, where the temperature is low, the relaxation modulus is high and pretty constant until it reaches the TG, which gives us that long range motion. And so we see that they have a decrease in the relaxation modulus, and then it kind of levels out, but then has another decrease once we get to more of a viscous liquid at the much higher temperatures. So we see a large decrease in this relaxation modulus at temperatures above TG. And so just to kind of put that in perspective, here are some TGs for various materials. So for the polyethylenes, like I said before, these are really low temperatures, so we're always above that. And then some of these other ones, you see that we would have to get closer to 100 or above degrees Celsius before that large drop would occur. All right, so we've just seen that the relaxation modulus can decrease with increasing temperature. So it has this temperature dependence just like we saw here. And so this is kind of showing you the relaxation modulus, but the log of it, so huge differences in those. And then all of these are at different temperatures. So T1 is the highest, T1 is the lowest temperature, so you see that it has the highest relaxation modulus, and then as we decrease the temperature, as we increase the temperature, we see that the relaxation modulus decreases, and you can kind of see the time dependence of all of these. So the relaxation modulus is always going to decrease, but it's doing that more so at the lower and lower temperatures. At the higher and higher temperatures. Keep getting that mixed up. And again, that's directly related to what we see here. So this is a function of temperature here. This is a function of time. So it's showing the difference between relaxation modulus and time, and then all of these are the varying temperatures. And so this is the one of the ways that we can measure viscoelasticity in polymeric materials is this relaxation modulus test.